Good afternoon, everyone. Let me know if I'm audible.
Good afternoon, sir.
Thank you. Last class, we discussed asymmetric key using RSA algorithm. And today we'll look at Diffie-Hellman algorithm. Your textbook has very sketchy view, very minor details without giving you any much background. So I probably work out a lot more so that you can understand how the really algorithm works. And then you can read the textbook to understand and assimilate the knowledge given. Primary purpose of Diffie-Hellman algorithm is that we would like two end users to agree upon a shared key so that they can transmit information. This shared key has to be derived, computed in real time, and they may not be able to talk directly. Their communication may go through number of people, and these two people have no advanced shared information which they can make use of. Everything is a start for us, and whatever they are communicating, anybody could see what they're communicating. But from there, one shouldn't be able to infer what is being communicated. Because messages go through many routers, many hubs, and if anyone can do packet capture and look at what is the data being communicated. And with all this information, intruders should not be able to discover, identify what is the shared key. And if you can derive upon a shared key, then they can use subsequently for their data communication. Applications, we have setting up a VPN, IPsec VPN, Microsoft L2TP VPN, or even the SSL, HTTPS, you name anything. So the first scheme was proposed in 76, and in fact, there was secret communication, but RSA with reverse Diffie-Hellman was officially published, so they got the name. And this method is a real practical method which has been used today to agree upon shared key among the two users, even in the presence of others. And now it's being used all across the world, different products, different things. The fundamental underlying concept that is used in the Diffie-Hellman key algorithm is what is called discrete algorithms. I'll talk about it in a short while, explaining you what a discrete algorithm is, whereas the textbook doesn't talk about much. They just talk about what is to be done, giving you some basic information. I'll give a little more detail there. We cannot use public-private key for exchanging messages because public-private key is very compute intensive. So practically can be used to encrypt and decrypt messages. That's why the public and private keys are used to only agree upon a shared key, and then that shared key is basically used to encrypting the message. So we'll basically look at how does communication happen. As you said, the whole mathematical theory lies behind discrete algorithms, which is based on a modulo prime. We'll look at that. Let's look at a simple analogy and assume that Alice and Bob want to share some secret key without prior knowledge, and the message has to go through a number of people. I have given some people here, A and B. Message goes through whatever Alice communicates. These persons can see that we're assuming that they're not the eating away, not sending. So they can see and then transmit. We look at the problem, this approach later, but currently assume from Alice it goes to person 1 to person 2 to Bob. Bob can communicate back. So Alice and Bob should be able to agree upon a shared key without these two people in the middle or anybody in the middle is able to agree upon. Any thoughts how this could be done? I'm trying to give a conceptual analogy, and using that conceptual analogy, we'll see how the same thing could be done using mathematically and using the different modular arithmetic. Let's consider that L is agreed upon as some value and say this value you would like to use. So this is the envelope which contains or whatever message, plain text message, which contains the her said key some information. If Alice communicates this message, people could read. And that means she cannot send this message. If she encrypts this with certain key, Bob does not know the key, so Bob can't decipher it, neither Bob nor the intruder. So what is the mechanism that can be used? And this information you will not find in a book. The animation I'm trying to provide so that you understand the whole concept behind Diffie-Hellman key exchange. So what Alice does is takes the key, puts in a box, and box has provision for two locks. And that means she can put one lock, and other lock can be put by Bob. But keys of the lock by Alice has the key of her lock, Bob would have key of her lock. So Alice takes a box with provision for putting two locks. Alice put the message in the box or the key in the box and puts her lock. Now she has the key, Bob does not have the key at all. Only Alice can open that lock. So let's see with this kind of thing how Bob can get the message. Alice sent the box to the user one because it has to go through one. Because the box is locked, user one can't open it because key is with the Alice. Presuming lock is strong. User 2 gives to user 2 and it goes to the Bob. Bob also does not have a key because there is no pre-shared information. So Bob also cannot open this lock. However, what Bob does is, because there is a second place, Bob puts his own lock onto the box. Now the box has two locks. First lock is Alice, second lock is Bob. Bob has his key, Alice has one key, and Bob putting the second lock returns it back to Alice. It goes via the person 2, then person 1, back to Alice. Because box has the lock, intermediate persons can't do anything. Now what Alice does, Alice can remove only her lock, but Alice cannot remove the Bob's lock because Alice doesn't have the key to the Bob's lock. So Alice removes her lock, sends the box back. Person 1, person 2, it comes to the Bob. Bob has the key of this lock. Bob removes the lock, gets the key, and now see Alice and Bob had agreed upon a key. It requires three-way communication, but having done that, even though the message passed through intermediate users, they could not get the key. They only became a transmitter, and Alice and Bob shared upon a shared secret key. This is the basic concept that is being used. That means when you share some information, sender or user one should put his or own lock. Other person should put his or own lock and exchange information, and using these two locks, somehow they should derive the information and agree upon a shared key. And that is the approach that is used by Diffie and Hellman algorithm. And let's look at that. Any questions about this approach? Anyone who has not understood how the two people can share the shared secret key among two, despite those people are in the middle, because they're using two lock mechanism. Now let's first look at the discrete logarithm which is being used, and we'll see why that is being useful. We know a prime number. A prime number is a number which cannot be factored or which has no roots. In discrete logarithm, we call primitive root of a prime number. We are going a little deeper in mathematics. So basically, for a prime number p, find out a number such that when we generate the powers of that number, subsequent powers, power 1, power 2, power 3, power 4, all the powers doing modulo p will give me all integer ranges from 1 to p minus 1. When that happens, for example, we choose a number a mod p would give me some value, a square mod p would give me some value, a cube mod p will give me some value, a raised to power p minus 1 mod p give me some value. I have the p minus 1 numbers, and these will give me basically 1 to p minus 1. If that happens, then a is called discrete logarithm of basically the primitive root of a. So a is called primitive root of prime number p. I'll give an example. Consider prime number 7. And let's say consider primitive root 3. Now 3 raised to power 1 mod 7 is 3. 3 raised to power 2 mod 7 is 2. Okay, 3 raised to power 2 is 9. 9 mod 7 is 2. Then 3 raised to power 3, 27. 27 mod 7 is 6. 3 raised to power 4 is 81. 81 mod 7 would basically give you 4. Because 7 into 11 is 77. 81 minus 17 gives you 4. 3 raised to power 5, which is 243 mod 7, gives me 5. 3 raised to power 6 is 729, and that gives you mod 7 is 1. So you look at 6 powers 1 to 6, gives me numbers 1, 2, 3, 4, 5, 6. We got all these numbers. That means 3 is primitive root of prime number p in our discrete logarithmic work. Any questions about understanding what is primitive root of a prime number? Can you find a primitive root of 5 or another primitive root of 7? Spend 2 minutes and see, can you find primitive root of 5? That means 2 power 1, 2 power 2, 2 power 3, 2 power 4, mod 5 should give the numbers 1 to 5. Or whatever the number is. Spend next 1 or 2 minutes, compute another primitive root of 7, compute primitive root of 5. Let me know if you are done. Anyone done? Susan?
Sir, doing sir.
Lokesh?
Yes, sir.
Yeah, could you figure out primitive root of 5?
So I'm trying, sir. I'm trying, sir.
Okay. Okay, let me put it this way. Is 2 a primitive root of 5? Or is 3 a primitive root of 5? Can you verify?
No,
Look
sir.
at all the powers of 2.
No,
2
sir.
is not a primitive root, sir.
Why say
Neither
Nikita?
is 3, sir.
Yes, sir.
Why not?
So because 2 mod 5 is 3 and 2
No,
cube
no,
mod of
no.
5 is...
Hold on, hold on. 2 mod 5 is 2. Why 3?
Oh, sorry, sir. Yeah, sorry. So the values are repeated, so it's not primitive.
Tell me. So 2 raised to power 1 mod 5 is 2.
Yes, sir.
2 raised to power 2 is 4. Mod 5 is 4. Are you there?
Yes, sir.
2 raised to power 3 mod 5 will be how much?
8 mod 5 would be
3.
3.
2
Great,
raised to
sir.
power 4
Great.
mod 5 is how much?
1.
1.
1. You got all the numbers? 1, 2, 3, 4. 2 raised to power 1 gives you 2. 2 raised to power 2 mod 5 gives you 4. 2 raised to power 3 mod 5 gives you 3. 2 raised to power 4 mod 5 gives you 1. You got all the numbers 1 to 4.
Yes, sir. Yes,
That
sir.
is 2 is a primitive root of 5.
Yes, sir.
Can you verify about 3? Is 3 a primitive root of 5?
Yes, sir.
3 is also primitive root of 5 because 3 raised to power 1 gives me 3. 3 square mod 5 gives me 4. 3 cube is 27, mod 5 is 2. 3 raised to power 4, 81, mod 5 gives me 1. I get all the 4 values. So both 2 and 3 are primitive root of mod 5. I mean the primitive root of 5. Similarly, you can try other numbers and look at what are the primitive roots. Having understood that you can find primitive root, now we look at some basic algorithm. So if we know that a raised to power I mod p is equal to b, then I is called discrete logarithm of b. And what we are saying is, for a large number, finding a discrete logarithm is a very tough problem. Knowing that is fine, but computing would be tough. And we denote I as d log a p b. So if a raised to power I mod p is b, I is called discrete logarithm of b. And that is the property we'll use to do our concept. So the whole algorithm, the way the algorithm works, let's say two users A and B wants to share a secret key. What they do is they choose a publicly known number. One number is a prime number, which is a very large number, and other is called a primitive root of P. And this number P and alpha are known to everybody in the world. So both user A and B can talk and say, let's use this as a number, let's use primitive root I, like this is 7 and 2, or whatever. So they choose a large P and some primitive root of P of alpha of P, and this is agreed upon. So this P and alpha is known to everybody in the world, not even the Bob and Alice, but everybody. Now the where the algorithm plays the role is following. User A selects some random number, any number feels like, less than P. So user A selects some random number called XA, which is less than P, and computes alpha raised to power XA mod P. This XA number is known only to user A. This XA is not shared. But user A computes alpha raised to power XA mod P, and let's say that number is YA. Alpha and P, alpha and P are known to everybody, is known to user B also. User B also does select a random number XB less than P and compute YB alpha raised to power XB mod P. Alpha is known to everybody, P is known to everybody, XA is known only to A, XB is known only to B, nobody else. XB computes YB, XA computes YA. What user A does is sends user A does YA, sends YA to B, and user B sends YB to A. So user B is sending the computed value YB. User A is sending its computed value YA to B. User B is sending YB to A. That means intermediate users can also know about YA and YB, but they cannot figure out XB because XB will become primitive root. That's what we said, discrete logarithm. And it is very, very hard to compute, even today when P is large, to compute the discrete logarithm. Now what user does is, user A got the value YB. YB was the value computed by user B. This value sent to A, and YB could be seen by everybody. Then user A does YB raised to power XA. XA is known only to user A. XA is not known to any other user, it's only to him. Similarly, user B computes YA power XB. YA is the number which user A computed. And YA is known to everybody either. But XB is known to user B. So user B computes YB, sends to A. User A computes YA, sends to B. And then user A computes YB raised to power XA mod P. And user B computes YA raised to power XB mod P. XA is private to A, XB is private to B. And the property of discrete logarithm shows that the two values K and K dash would be the same. And these two values becomes the shared key, which nobody could agree because XA is private to user A, XB is private to user B, and all these people in the world, they know alpha, they know P, they know YA, YB, but because they don't know XA and XB, computing XA would require discrete logarithm, which is hard to compute for a large number, and hence can't be computable. And using this mathematics, they can agree upon shared secret key. And that is what, so look at the proof. How does K is equal to K dash? So K is computed by user A. He gets YB, which is power XA mod P. Now what is YB? YB is alpha raised to power XB. This should be mod P here, typo error there. And then we know alpha raised to power XB mod P power XA. So let me correct it here. Sorry. Alpha raised to power XB mod P power XA. This basically becomes alpha raised to power XB XA, which is alpha raised to power XB XA, which I can write as alpha raised to power XA power XB. This can be written as alpha raised to power XA mod P power XB, and this number is YA power XB, which is what is K prime is, computed by user B. So whatever user A computes, whatever user B computes, two are same. XA is chosen by user A, YB is chosen by user B, and when they compute exchange, they get the same value, and this becomes shared key. And that is the beauty of diffie element key exchange, that even though information is shared in public, the shared key cannot be tracked. So the way algorithm works, all users agree on global parameters. What are the global parameters? Prime number P and primitive root alpha. So they agree upon these two numbers. And probability is that for every integer which is less than P, that's 1 to P minus 1, more. When P is a prime number, GCD of A and P would always give you 1. P is prime meaning no number less than P can divide it. That means greatest common divisor of A and P always 1, where A is less than P and greater than 0. So in that case, now we have those numbers. So alpha and P are known to everybody. And we know that because of property, when A is alpha is primitive root, for each some power of k, I'll basically get integer k. So 1 to p minus 1, I'll get the value. So each user then picks their own number xa less than p. User B picks the number less than xb, and xa less than p, and user computes ya is equal to alpha xa. User B computes alpha xb, and you have a shared session key, which is, sorry, this should be alpha. Too many typo issues. And that's the way algorithm really work. And you got a shared secret key. Now, only first challenge is P has to be large number, where alpha can be small. Doesn't really matter what alpha is. As long as P is large number and both X and XB are large number, when you compute YE and share it, it is not computationally feasible for hacker to determine the shared key. An attacker needs to determine only if it can solve discrete logarithm problem, and which is a hard problem for large numbers, cannot be solved. Computationally infeasible, and then the two users have relied upon a shared key. Let's take an example there. Let's say prime number P is 353. Let's choose primitive root alpha is 3. Now let's say user A chooses some number which is 97. So user has chosen the number 97. 97 is less than 353, can choose any number. Computes YA, which is 397 mod 353, and this value happens to be 40. Let's say user B chooses another number, which is 233. The numbers could be same, numbers could be different. They're picking any random number, doesn't really matter. User B computes 3 raised to power 233 mod 353, which becomes 248. So A sends value 40 to B, B sends value 248 to A. How do they write the key? When A gets the value 248, A would compute 248 power 97, because that is what the key would be. So A computes 248 is what given by B, power 97 is number, mod 353, this gives a value 160. Similarly, B computes 40 raised to power 233, because A sends the value 40. 40 raised to power its own number 233, mod 353. This value also comes to be 160. So 160 becomes the shared secret key. Now for attacker to solve, attacker must find out what is 97 or what is 233. So attacker knows that the 248 is known, attacker knows the 353, but attacker doesn't know to computing from this value 248 and 353, attacker cannot find out 97 for a large P. And that is where security gets implemented and attacker can't kill these. These being a hard problem, and that is how the Diffie-Hellman algorithm basically works, using a shared secret key. However, if you look at in real life, this algorithm is implemented with some modifications, because this algorithm is vulnerable to man-in-the-middle attack. When B is receiving a key, B hasn't verified that key is actually coming from A and not coming from somebody else. And same is true for B. So there could be a man in the middle which could play the bad guy role and compromise. I'll give you the idea how that can happen. So consider our case, Alice and Bob, there's a man in the middle. Let's say Alice sends a box, puts a lock, sends to the person. What this person does is creates another box and sends that box to Bob. Bob thinks the box is coming from Alice, whereas the box is coming from middleman. Now Bob would send this box back. This person would send the box to Alice and vice versa. So this person would share one secret key between Alice and himself, and this person would share another secret key between Bob and himself. Alice would think this shared secret key between me and Bob, and same is true. So whatever Alice sends, he will decrypt and encrypt using shared key with Bob and send it. So this is the problem what is called man in the middle. Because man in the middle is problem occurs because end user not authenticating. So before you can agree upon key, you need to ensure there is authentication there, and that authentication solution is provided by using digital signature and public key certificates. So by itself, Diffie-Hellman key cannot be used because it is subjected to man in the middle. Someone in the middle can mimic and partition the two, and that way it works. So it is used with public key certificates and digital signature, so that Bob has to be absolutely sure that the message is coming from Alice and not from middleman. Similarly, Alice need to be absolutely sure that the box is coming from Bob, not some in the middle. And that is used in what is called using digital signature. And we'll study digital signature in our next class tomorrow. So yesterday we looked at asymmetric key. Then today we looked at Diffie-Hellman key exchange. And then tomorrow we'll look at digital certificate, which is basically authentication. We looked at cryptography, confidentiality. We also look at authentication, and integrity is because we are doing digital signature also would provide not only authentication, but also would give us integrity check as well. And that we'll study tomorrow. So I will recommend you take some prime number, work out some primitive root, verify that it works, take any two numbers like what I have given. So take any prime number, find a primitive root, take two numbers and verify that algorithm would work. Understand that part, solve it out, and then you see this how the Diffie-Hellman key exchange would work. You need to practice, work it out, because I'm going to soon give you after whole module 4 is over, you'll get the third assignment, which will revolve around your Diffie-Hellman key exchange, public-private key, and all that matter. Computing that, this is what I would recommend. Any questions, please do ask. If not, I'm done for today. If no questions, thank you. You can drop out.